Hello everyone, my name is Chaya Le from Nankai University. I will introduce my paper, an efficient reachability query approach for large graph based on cluster structure. The contents of my speech include the following four aspects: introduction, algorithm, experiment, and conclusion. Nowadays, many real-world networks can be modeled as a graph, where vertices in V represent entities and the edges in G represent relationships between entities. The graph can be a directed graph or an undirected graph as appropriate. What's more, reachability queries are a fundamental operation on graphs and have numerous important applications, such as query processing on social networks, the semantic web, XML documents, road networks, and program workflows. First, we will give a simple definition of reachability query. Given two vertices U and V, a reachability query asks whether there exists a path between U and V in graph G. Then we will introduce the related work about reachability queries. Nowadays, there are lots of techniques for reachability queries on a directed graph. A common approach for these methods is to transform the input graphs into their corresponding DAG. DAG is a directed acyclic graph. Specifically, for any two vertices U and V in DAG, if U point to V, then there exists an order O, and OU is smaller than OV. This order will be a vital part to construct the reachability index. As a result, this method cannot be applied to undirected graph due to the non-ordering of undirected vertices. However, many networks can be modeled as undirected graphs. Take the email network for an example. We can treat each user as a vertex and consider the communicating between users as an edge. We use solid lines for the first relationships. For example, relationships between Jane and the people who appear in emails exchanged with him. For the second relationship, dashed lines are used to link contacts that appear together in the emails exchanged with Jane, or contacts who appear in the emails found in the body of Jane's email. In this case, we better use an undirected graph. But techniques for undirected graph are only a few, and they cannot handle very large graphs. Our target is to improve the ability to scale the large graphs, as well as reduce the processing time. In this paper, we propose an indirect graph reachability query algorithm by integrating graph clustering algorithm with traditional search methods. The key process of UGR is as follows. Step 1. We divided the graph G into clusters. Step 2. We generate a new graph G' in which each vertex was a cluster in G. Step 3. We compute the transitive closures of all vertices in G'. Next, we will detail each step. At present, a trend in dealing with big data is parallel processing, dividing the original data into small pieces, then separately processing each piece and merging at the end. By clustering graph, we can divide the original graph into pieces. In this paper, we cluster graph based on a state-of-the-art structural graph clustering method, pscan. First, we initialize all vertices in G. For each vertex U in V, we set U as non-corn vertex. At the meantime, we incrementally maintain an effective degree EDU and a similar degree SDU for U. SDU is the number of U's neighbors that have been determined to be structure similar to U. EDU is the degree of U minus the number of U's neighbors that have been determined to be not structure similar to U. We structure cluster graph through a two-step paradigm. Cluster corn vertex and then cluster non-corn vertex. For each vertex V adjacent to U, we compute the structural similarity between U and V. If the result is larger than a threshold value, then we decide vertex U and V are structural similarity and increase SDU by 1. Otherwise, we decrease EDU by 1. Once SDU is bigger than mu, we determine U as a corn vertex. On the contrary, once EDU is smaller than mu, we determine U as a non-corn vertex. In this way, the algorithm can terminate early without visiting all the neighbors of U. Furthermore, if V is a corn vertex, then we assign U and V to be in the same cluster. Then we cluster the rest of the vertex. We iterate through all vertex in G that has not been included to any cluster, and exclusive DFS to merge it with its neighbor. After clustering, each cluster can be self-connectivity. The second step is generate a sketch G' of G. First, we consider each cluster C in G as a vertex in G'. Then, given two clusters C1 and C2, if there exists an edge between C1 and C2, then add a new edge between V1 and V2. Cluster C1 and C2 corresponding to the vertex V1 and V2 in the graph G'. Let N and M be the number of vertex and edges of graph G, and let C be the number of clusters. After clustering, the graph can be scaled down to OC. Finally, we use DFS on new graph G' to compute the transitive closures. After that, for any vertex V in G, we can be aware of the set of vertex that we can reach. We let FC be the transitive closures of C. At the query time, given two vertex S and T in G, we first seek the vertex S and T in G', which contains S and T. If S is the same vertex with T, then we return true, which means S and T can reach each other. Else, if Fs contains T, then we return true. Else we return false, means Fs and T cannot reach each other. The query time complexity is O1. In order to demonstrate our analysis, we implement our UGR method and compare it with traditional search method, DFS and Warshall. We evaluate the graph on 5 real datasets from the Stanford Network Analysis platform. Table 1 lists the number of vertex and edges in the graph, and Table 2 reports the construction time of processing. We only evaluated the performance of Warshall on the first 3 datasets because it obviously slower than others. What's more, when the scale of data size is small, DFS had better performance. However, it ran into stack overflow on the last 2 graph plots. Experiments show that UGR is more scalable and stable than traditional search methods, especially on sparse graph. At last, we make a conclusion. This paper presents a study on reachability queries on large undirected graphs. UGR is more scalable and stable than traditional search methods, especially on sparse graph. For future work, this work can be extended in several interesting directions. First, we will study the evolution of graph shortest path search queries. Second, we will improve the clustering method and make our approach apply to the weighted graph. Third, we will exploit the distributed database to achieve higher scalability in terms of graph size. That's all. Thank you for listening.